Alright, so last thing I really want to go over this unit is just to summarize everything we've done on quadratic so far. How do we graph the transformation of a quadratic function? So a transform quadratic function will look like something in vertex form. So remember, it'll look like y equals a bracket x minus h all squared plus k. Okay, where remember h and k are your vertex, and a gives you direction of opening and also helps you see how narrow or wide the parabola is. So, in referencing to what we did last lesson, the first thing that you're always going to want to do is take key points off the original quadratic function. Now, 99 times out of 100, the original quadratic function is y equals x squared. Okay, so what are some key points that are on y equals x squared? Okay, well, if you think about the graph, okay, so here's a graph of y equals x squared, and you can see from the table of values, these are some key points that are on there. So you always have the vertex here at 0, 0, and some other key points that you can commit to your memory for the graph of y equals x squared are these ones right here. 1, 1, 2, 4, negative 1, 1, negative 2, 4. So these are going to be the points that we start with when we're trying to create a graph. Okay, and once we have those points, what we're going to do is we're going to create the mapping rule from the original quadratic function to the new transformed quadratic. Okay, so we took a look at that last lesson. From the equation, you should be able to recognize a pattern to create the mapping rule from there. So what's happening to all the x values, what's happening to all the y values. Okay, and the reason we have that mapping rule is because now we can take those original points, the ones that we took from y equals x squared, throw them into the mapping rule, and what the mapping rule will spit out for us is what we call the image points, so the corresponding points that will be on your new transformed quadratic, so the equation that they gave you. Okay, once you have that, it really just becomes very simple to get your graph because you'll have your points, then you can plot them on the grid. And then the only thing that's left is just do a double check to make sure you haven't made a mistake by checking that the vertex is in the right spot, that the direction of opening seems to make sense based on your a value, and that your overall shape looks like a quadratic. If you have a graph that looks like it's a little bit off in terms of a shape, you've probably made a mistake somewhere, either with the plotting or with the mapping rule or calculations. Okay, so just things to keep in mind there. Okay, so let's do one together. So here's the example of a quadratic in vertex form. So I'm starting here with my 5 key points from the original quadratic, which is y equals x squared. I'll just make a note of that here. Okay, and let's try and create a mapping rule here. So remember your mapping rule, the only thing that changes your x value is what's inside the bracket here. So remember our vertex here is actually going to be at -3, +8. So that means in terms of a transformation, I move to the left 3, which means my mapping rule I have x minus 3. Okay, so for the y value of my mapping rule, I have an a value of -2. Okay, so that gives me a reflection and a vertical stretch of factor 2, so I have -2y, and then I'm shifting up 8 from there. So that gives me my mapping rule. Okay, once I have that, I'm off to the races, because I can take these key points from y equals x squared, throw them into this mapping rule for x and y. So I'll do one with you here. So let's just say I'm using the point -2, 4. So if you use the point -2, 4 into my mapping rule, all I'm doing is replacing the x value with the x value of the point, -2. So I get -2 minus 3. Okay, and the y value of my point 4 goes into y in the mapping rule. So I have -2 times 4 plus 8. Okay, and just a matter of simplifying from there. So -2 minus 3 gives me -5. So actually give me the x value of my new point. And then for my y values here, -2 times 4 is -8, plus 8 gives me 0. So that tells me on my new graph, so the original one here, y equals -2 bracket x plus 3 squared plus 8, I have a point at -5, 0. So I can plot that point. Okay, so what I'd like you to do now is take a minute and repeat this process for the 4 remaining points here, and see if you can get 4 new image points and try and create your graph. Okay, so give that a try and push play and ready to see the answer. Okay, so you can take a look here and see where I got my image points. If yours don't match up, then check your math again, see that I've made a mistake, and if you can't find it, ask me for help. So I plot these 5 image points now. I want to see if everything seems reasonable. So does the shape seem to resemble a quadratic or a parabola? Yes, it does. My vertex here is at -3, 8. Does that match what I would see in my original equation up here? Yes. This one parabola opens down. Is my a value negative? Yes, it is. Everything seems to make sense here. So all that's really left at this point is to connect my points with a smooth curve, put arrows on the end to indicate that this is going to continue on forever, and there's a graph of my parabola. Okay, so anytime you're asked to make an accurate graph of an equation in vertex form, this would be the approach. So you can take your points from y equals x squared. They're not going to change. Find the image points using your mapping rule, and then plot them. One thing you may be able to potentially do to save some time, you'll notice here that since parabolas have symmetry, you only really need to necessarily do these 3 image points to generate these 3 right here, and then you could use symmetry to determine the other ones here. So let's say I only had -3, 8, -2, 6, and -1, 0. I could use a symmetry to generate that point and that point as well. So just something to keep in mind if you're looking to save yourself some time. Okay, so let's move on. Just going to tie some domain and range into quadratics, and that's going to be it for the unit. So here's a couple of quadratics. I want you to find the domain and range for each one. Now, remember, domain is a list of all possible x values inside a function, and the range is a set of all possible y values that are part of a function. So in this particular, it really helps to have a sketch of what's going on with a graph, so you can visualize domain and range a lot easier. So just by looking at this function here, you can probably tell me a couple things. You can tell me the vertex is at -55, -12,500. Okay, and from the a value being negative here, you can tell me that this opens down. Okay, this information, the vertex and the direction of opening, is all we need to find the domain and range. And I'll show you how. So let's take a look at a graph. And you don't have to make a graph scale. It's just going to be a really, really quick sketch. So I'm going to have a vertex at -55, -12,500. So in terms of the quadrant it lies into, -55 is to the left, -12,500 is somewhere down here. So this is where my vertex is, somewhere in the bottom left quadrant. Okay, so with that in mind, as long as I open down, I get an idea for a sketch. And I should be able to get my domain and range from here. Now the domain, well, parabolas continue on forever to the left and right, so my domain is quite simple. We're just going to say for the domain that x is an element of the real numbers. Okay, the range is a bit more complicated because you'll see that the graph does not exist above the vertex here because we open down. So what we need to look at is the y value of the vertex here, which is -12,500. Okay, and then we notice that the graph only exists below that, so we'll say the range is that y is less than or equal to -12,500. Okay, so once you have a sketch, the range becomes much, much easier to see. So I'd like you to try and do the same thing here. We've got another function g of x. See what information you can get about the parabola just by looking at the equation. Make a very, very quick sketch and see if you can find the domain and range for that one. Okay, so give it a try and push play and ready to go through it together. Okay, so you should have gotten a domain for an answer of x is an element of the real numbers, because it is a parabola that continues on forever from left to right, and my range is that y is greater than or equal to 85. So again, just to see where I got this from, make a very, very rough Cartesian plane here. My vertex is at 125 along the x, 85 along the y. So 125 on the x, 85 on the y is somewhere up here in the top right quadrant. This particular parabola opens up because the a value is positive. So in terms of a general sketch, we look something like this. So again, my domain is an x and element of real numbers, but the y value of my vertex here is 85, and this graph only exists above the y value of the vertex. So any y value in the function is going to be greater than or equal to 85. Okay, so hopefully that makes sense. That's it. That's all for this unit. So there's some questions there from the textbook. That'll make really, really good practice, and then we'll start getting you guys ready for a quiz, review, and a test. Okay, cheers.